Hi viewers, welcome back to the Multimagic channel. Myself is Funny. I hope everyone are following this audio series. So far, we have uploaded 3 videos in this audio series segment. Where the first video talks about basics of audio, and the second video talks about how to capture raw audio using port audio framework, and the third video talks about how to convert a raw audio into a AMR format or an encoded AMR format. Okay. Uh, this video will be this fourth video in this particular series segment will be very interesting because today we'll be covering a topic called how to capture audio raw data and encoding using AMR in real time. So I will talk about what is this real time, why I am using this term real time. So let's start with the content first. So first thing first, we start with our agenda today. So let's quickly focus on the prerequisites to run this project, and then we'll also have a quick glance at what we have done in the earlier video, and then I will talk about little bit introduction to what is expected from this particular video, and also how I will also talk about how to capture and encode in real time and code flow, GitHub links, and upcoming projects. So this is the basic agenda I will be covering in this particular video. So let's start on this note. So yeah, prerequisites of course. So for this particular audio series, we are using this particular platform Windows. And architecture is x86, and the integrated and development environment we are using this Microsoft Visual Studio 2010, and of course, and above also you can use. I am using MSVC 2022, and the third party libraries needed for this particular project is Port Audio, which is for capturing the audio from the mic, and OpenCore AMR for encoding. So these are the two third party audio libs needed. Of course, as I mentioned from the beginning of the series, this particular project is not built from the scratch, but we are using a particular project which has been developed by our mentors during their pre-startup days. So I just recompiled it in this particular Visual Studio, MSVC 2022 version, and the libraries, for the simplicity point of view, the libraries of these third-party libs, OpenCore AMR and Portaudio, I am just using the same version at the time the project is built. I think couple of years back. Yeah. So this is about the prerequisites for this particular project to run on our machine. Okay, so far good. So now let's quickly recap what we have done. So I want to quickly see what is our project one and project two. Project one is where we capture raw audio, and these are using port audio framework, and these are the specific APIs we are using. And one thing we need to remember is open stream. We are not using any callback, and the read stream and write stream are blocking APIs. So I will mention about the specific terms. Of course, most of the people know about this blocking API and non-blocking API, but I will give a quick intro on what is about blocking API and what is about non-blocking API. And about project 2, this is about the uh, capturing encoding the raw audio to AMR format. And here we are using OpenCore AMRs, and these are the APIs we are using. Okay, so let me quickly show you those block diagrams also to make it clear. So here we are simply this is the project one. We were capturing the audio data, and then we are saving the samples into the buffer, and finally that samples we are writing into the file, and these are the validation things. But to make it very simple, we are capturing the data and saving it into the file for the testing period 30 seconds. That is about project 1. And project 2, it is very simple. There is already a file, there is already specifically a raw data file which is located physically on your machine. We are reading that file, and then we are actually saving that into we are reading that bytes from that file and saving that into a buffer, and in that buffer we take a particular frame. How we define this frame is already we discussed in the last video. This is the spec for the metadata, and we take one frame, and this particular frame we encode it, and we write into this file AMR file like that. We iterate through each frame and then we write it into the file. And these are the APIs used open for AMR APIs. And this is the metadata. So this is just a quick overview of what we have done in project 1 and project 2. So why I am discussing is because that sets the context for this coming video now. I mean the next slides in my opinion. So now, see, let's say, yeah, this is really interesting actually. See, if you want to, in general, real-time audio applications, capturing and encoding must be done in a single application. Okay, so you should not maintain two separate projects. Like, okay, I have project one, I have project two. I will use this application. I will use this application. That doesn't make any sense here. So we don't we don't need two individual applications running on the same machine and doing one actual purpose. So now, what if let's say we want to do uh, capturing and encoding at the same time. So that is the real-time application. So we capture, we speak, and the data is encoded parallelly and is written into the file. So everything is happening in parallel. So from general approach, can we mix these two building blocks? In a sense, can we mix this project one and project two? So I have given a thought on it. So this is how the block diagram looks like. Okay, so this is if you want to capture raw data and simply you write to the buffer. So don't write to the file here because we don't need the raw data to write into the file. We just need only the encoded format written into the file. Into the yeah, only the encoded data called AMR file or .amr extension file. So this particular project is just to capture the raw data and encode it and then write into the file. For that purpose, I have clubbed these two projects 1 and project 2, but instead of writing it to raw file, I'm just only writing the encoding file. So before moving on to the disadvantages or more details on this general approach, let's quickly recap on two specific terminologies called blocking API and non-blocking API from the software context point of view. See, if you talk about blocking API, a call to blocking API will cause the program or thread to wait until the operation is completed. In another way, if there is a call A and call B. So if call A is a blocking, it means let's say for call A to execute, it takes 10 seconds. So after the 10 seconds only, the call goes to the call B. Okay, so that is simply blocking API. So non-blocking API means there is a function A and there is a function B. So after calling function A, it doesn't necessarily wait until function A gets completed. It moves to the next function B. So this specific mechanism is called as non-blocking API. So you can see here they typically return immediately, allowing the program to continue with the other tasks. It means it is not blocking your rest of the task here where it is blocking the other operations until the current operation is completed. So this is about blocking and non-blocking technologies from the software context point of view. So now let's see all together what is happening now. See, this is what I am telling. So this is a single project where we are capturing and then encoding in parallel. Let's see what it happens from the sequence point of view. Let's say your application started and you did all the initializations open stream, and once you did open PA open stream, there is no callback associated. Finally you start the stream and the application sends this API to port audio framework, and here you will get a stream is open, and in the stream the data is coming live, okay, from the mic. So what happens is, I mean, it yeah, not from it, yeah, data is about to serve, the stream is open, okay. So now once when you start, it is open and data is coming here, and once you pick call this particular API read stream, it continuously reads from this stream immediately. So as per this spec, we'll first read the first 160 samples. P, as I mentioned in the previous slide, the first slide, this read stream is a blocking API. And here we have seen the meaning of blocking API means it will block until the next execution. So until this 160 samples we got, uh, the read stream call will not be get handed over to the next set of call. Okay, so now after this 160 samples got convert this 160 samples, now these are encoded here, and then finally we return into this AMR file here. Okay, so now again a read stream will call. So this read stream is called for every frame. So as we have seen in the previous diagrams, I mean in the for every frame we are calling the read stream. So here we have read stream, and then read stream means it reads from all the samples from this input stream, and that how many samples it will read? 160 samples. This is the configuration we have given, and now these 160 samples are now encoded here. Now by the time if you go to the next read stream, by the time already the samples are there here, and then there will be a loss of data here. It means it took the time it took to encode and then to return into the file. In that time we lost the data whatever that is coming in live from the mic. So this particular sequence approach, where if you just simply club project 1 and project 2, like where you capture it, you return into the buffer, and then you read from the buffer, and then you later encode it. So in this particular in this particular flow, what happens is there is a possible loss of data, is because here we are only depending upon a blocking call where only a specific samples are read, and then in the next flow after samples are read we encode it. So during this time other samples already came into the picture, but we ignored it from this stream, and then we took from this point the 160 samples. So finally we are not converting the entire captured data into encoded data. So this approach will not fit in the real-time application. Okay. So as we discussed, the disadvantages are it is time consuming, loss of data, and then real-time capturing and encoding cannot be done in a single thread. In generally, we need multi-thread application. We are coming to that point, and also the code is tightly coupled. So to solve these type of things, we use a callback mechanism. So from the software context point of view, a callback function is just a function that is passed as an argument on their function. The function receiving the callback then call this function at some point later. So it means that the callback function should be received, should be registered as an argument in calling function, and that particular callback function can be called later. So these are which are commonly used in event handling, asynchronous programming, and scenarios where you want to decouple the components of a system. So this is about disadvantages of the current approach, and to overcome this, we are introducing a callback mechanism, where callback mechanism allows you to run things in parallel or in asynchronous way. Okay, so now let's see how this helps us to overcome the loss of data. See, now this is what happening in case of callback mechanism. So we have application. Okay, during PA open stream only, we need to register the callback. Callback means the functionality that should be triggered at certain point. So that function is nothing but now the encoding thing, encoding the raw data to AAC. Okay, so now we just start the stream. As you know, once you start the stream, Port Audio Framework, all the samples are in the stream now. So now what happens is, as we're associating this callback to this open stream, once the stream starts, see the portrait is designed in such a way, the callback is designed for every frame. So this configuration also we can set in the code that I will tell in once we go through the code flow. So for currently, all you can remember is the port audio framework is designed in such a way, for every frame or for every 160 samples, we can call a callback mechanism. That callback function which is registered during the PA open stream. So this callback function, what it does simply, we just simply take this 160 samples, and then it encode that, and finally return into this AMR file. Okay, so it happens for the next 160 samples also, and then it then encodes and then converts this into the AMR format. Okay, so here this particular PS start stream, it is non-blocking call. Non-blocking call means it doesn't wait until all these things are done. It just simply start the stream and it returns simply. And after this thing is done, the callback functions runs in a separate thread. So this is the thread which is created by the port audio. So now simply it starts this port audio framework. Now whatever buffer we get here, so that buffer is exposed to this callback function. In the other way, this callback function has the arguments where the input buffer is one such argument. So this buffer gets exposed to the application, and then these values are encoded. So we need to ensure this particular process it is done when the next 160 samples are already called. Okay, so that has been already taken care, but that is the typical callback uh, functionality. So the execution time of the callback should not be too long, such that it will be not doing its actual purpose. So it should be ensured that you try to avoid printfs, locks, and very heavy loops inside this callback function. Just make it simple, straight away write exactly what you want, and that will help us to ensure it will execute in less amount of time when it is ready to collect. And I mean, when the next 160 samples is there, this callback triggers properly again. Okay, so I just quickly recap on this here. So to avoid the loss of data, we are going to a callback solution where this application open stream is there, and then register the callback. And then once you start stream, for every 160 samples, that callback mechanism gets triggered, and the callback functionality it just encodes this 160 samples and return it to the AMR file. And again from the stream, it reads the next 160 samples, and this since the samples are ready, it will callback is called, and this particular buffer is again passed to this AMR encoder, and then it just appends to this AMR file. Okay, so like that all the frames are encoded and written into the AMR file. So here you can see things are happening in parallel. So this is the visualization we can. So we are talking, so our raw capture is generating, and for every 160 samples, this particular buffer is passed to the callback, and the callback will pass this to AMR encoder block, and this particular frame is encoded, and the encoded data is written into the file. And these things are happening in parallel. So 160 samples you get, trigger, reframe, and again come here, the samples you read, and again it triggers callback, encode AMR. So it is like read, encode, write to file, read, encode, and write to file. So this particular three operations are running in parallel. Okay, so this is how the callback mechanism helps us for enable capture plus encoding together in a separate threads. So why I'm telling separate threads is because here this particular callback thread is responsible for encoding, and this particular port audio framework is or this particular entire application thread or main thread is responsible for capturing the raw data from the mic. So this is a kind of multi-threaded with, I mean, multi-threaded in the sense callback mechanism is running on a separate thread. So in that way, we can also call this as a multi-threaded program, multi-threaded approach, or a callback mechanism approach. So I hope I am clear so far. So next, move on to the next things. So now I will simply discuss about the code flow. So firstly, we need to define the specs. Okay. So how the raw data should be generated. So as we discussed in the previous videos, these particular parameters are aligned to the AMR encoder. If you give here different parameters, you cannot properly encode the raw data. And this is the callback function I'm talking. So as you can see in this callback function, the input is the buffer. So the buffer is nothing but during the PA open stream. In PA open stream, you are telling you are associating this callback, and then here you are taking samples for frame, which is nothing but for every 160 samples you are calling this callback function. So this is the callback function. So the callback function simply reads this data and then it simply encodes the data, encode PA data, port audio data. Okay, so this is the spec, this is the callback function, and how frequently this callback function is called is defined in the PA open stream, which is 160 samples. So for every 160 samples, the callback function is called. Indirectly, for every 20 milliseconds, one frame of audio data is encoded. So if you're talking continuously, for every 20 seconds, for every 20 milliseconds, the audio is encoded. Okay. So it is like you talk, you are encoding, you are talking, you are encoding, you are talking, encoding. So that particular 20 milliseconds is taken as a reference because AMR spec is like that. If you move to other encoder, this will be a different spec. Okay. So now this is about the initializing the port audio and registering the callback. Okay. This is PA initialize and then this is PA open stream. And then you are registering the callback here. This is the specifications. Okay. So the next in the code flow is initializing the AMR things. So that is about port audio things. For AMR, you need the void pointer and then you need to initialize the AMR encoder. And then after that, you need to encode the particular raw audio frame, whatever that 160 samples we got. So that 160 samples of data we are passing to this encoder and we are encoding with MR475, which is nothing but bit rate as 4.75 kilobytes per second, and this is the data we are sending, and this is the encoded data we want. Okay, so now port audio callback is called raw audio data is stored in input buffer, pass the buffer and let AMR encodes the encoded data. Okay, so once the data is encoded, we write to the file. So the first 6 bytes of the AMR file is nothing but a header, which tells that this is of the type AMR, and we will write the entire encoded data into the stream continuously. So first we'll get 160 samples we encode, and that encoded size will be close to 13. That data we are writing here, and then finally we are closing the stream after all the particular data is written. All the data is written. Okay, so this is what is happening. And finally, after all the things are written into the file, I mean all the things means unless if you do control C, our application no longer accepts the input. So until that point, it keeps on accepting. So once you press the control C, the stream closes, and then you will be exiting from the AMR library, and you will be closing all the strips, and you will be terminating from the port audio. So this is what happens. Okay. So just I'm reiterating again. So this is what happening. This is the callback solution which we have put in the picture to ensure capturing plus encoding happens parallelly without loss of any data. So stream starts, which means all the data, whatever we are speaking, it is available in the form of buffer for every 20 milliseconds or for every 160 samples. We simply encode it with the help of callback. This callback is registered, and once the callback is called, a subroutine thread is created, and subroutine is encoding happens. And in the main thread again, it gets the next set of 160 samples, and by the time a callback function is already done, it triggers the next callback, and then we encode it, and like that it goes on until user press the control C. We capture in real time data. We are speaking continuously, we are capturing continuously, we are encoding continuously. All the things are happening in parallel. Okay, so I hope I am clear until so far. So code flow we have already gone through. Okay, so now, so the next in the pipeline is about, I will show you the demo here. Okay, so this is what I'm explaining about. This is the code. So this is already available in the kit. So you can put breakpoints and all. This is the capture audio. I'm sorry. So in capture audio, where you will begin this thread, audio processing thread, and then in this audio processing thread, you just actually call this function, and here this is what you open the output file, and then you mention all the specifications, and then you stream open here where you just register all the callbacks, channel types, all those things, and this is the callback function, and this is about the specs. So everything is there in the GitHub, so don't worry. So now let's quickly first let me build the code. Okay, the build passed. I think I already built it. So let me start running it. Okay, so now it is opened here. So whatever I'm talking now, it is getting captured. So unless I give a interrupt signal. So here I mentioned, here I registered, yep, a signal. Yeah, you can see here printf signal control C. So once this interrupt is generated, the stream gets closed, and then the port audio functionalities terminates, and then it stops recording. Okay, so if you do control C, the input stream gets closed, to make it very simple. So now it's so far recording, and then now I will press control C. Let me see. Okay, it's still capturing. Okay, so now I pressed control C. The program has terminated. So now I'll just, the PA close stream has terminated. Once the PA close stream is terminated, the application also gets terminated with exit code as 0. So now this entire information will be in this particular folder. Give me a second, I'm pulling that out. Yeah, okay. So we go here, we go for audio video internals, AMR encoding. Yeah, okay. So this is our file, and this is the current timestamp. Okay. So this we can play back, and then let's see if whatever we speak.
So now it is open here. So whatever I am talking now, it is getting captured. So unless I give an interrupt signal, so here I mentioned, here I register TM a signal. Yeah, and see here printf signal control C. So once this press press control C, let me see. Okay, that is terminates and then it's.
So I hope you are able to hear that. So this is how in the real time, we capture the data through port audio framework, and we encode it without losing any data using callback mechanism or in a multi-threaded environment. I am sorry if in middle or here and there if I was not clear, but I hope I hope I am clear in the process of the video. If you have any questions or if you have any doubts, please mm, or you can contact us in the comment section, or you can go through our Multimagics blog and you can contact us. But the main intention here is to learn about how we can play with the different audio processing techniques. So in this particular video, as I discussed, so the main slide for this entire thing is this. So here we are just doing everything in parallel. We are capturing, we are encoding, we are writing. We are capturing, we are encoding, and we are writing. And which block we took, this all depends upon the specs. So if in the spec, if you define 320 frames, I will take 320 frames. Here I define 160, I am taking 160. Why 160? We already discussed in the last video, because the AMR works, encoding works on this particular specs. That's why we took that particular value. So hope I am clear so far. And then yeah, I think the demo is also done. And yeah, this is the GitHub links you can go through where the project is there. You can play around with and then see whether are you able to capture and encode parallelly in real time. And yeah, so the next couple of videos will be really very interesting. So it is on, so far we have did AMR encoding. So now we'll focus on AAC encoding using FFmpeg APIs. And then next we'll see one more project about how to mix two PCM datas. And we'll also go through one more project where how to create a audio file streaming service application. So this is something like called Spotify. If there is a file in the server and how to push the data into that server, or how to put the capture data into the, or how to start a streaming service application. And then if you simply want to uh, play it, how can you get all the data? So that will be really interesting. Okay, so I hope everyone thoroughly enjoyed this video, and then thanks all for following us, and thanks all for subscribing and for your viewing. Thanks a lot. See you again in the next video. Bye bye. Take care. Thank you.